This video is going to go through all of the molecules here in example 811 to decide which are dipoles, in other words, which ones are polar. You should have already filled in the notes on what makes something polar or nonpolar. I would also suggest that you pull out the molecular polarity flow chart to help you with these. So we went over a few in class, but we did not do all of them. So I'm going to do all of them here from example 811 and the two exceptions listed, just so you can see how these work for some extra practice. So whenever we're trying to determine molecular polarity, step one is still going to be draw the Lewis structure. Step two is going to be figure out the molecular geometry, and based on the way that shape is, that will determine whether we have a polar molecule, a dipole, where electrons are unevenly distributed, or a nonpolar molecule, where all the electrons essentially are being pulled equally and opposite and canceling out. So step one, pause the video right now and draw Lewis structures for all 7 of the molecules you see pictured here. All right, so here are all 7 of our Lewis structures. Now, if we were to go and label all of our molecular geometries, you could base it off the AXE notation. Once you do that, that will also help you decide whether you have a polar or a nonpolar molecule. So if you haven't already done so, go through all 7 of these and also label the molecular geometry for each of these molecules for extra practice. All right, check your answers for our molecular geometries. They're all there in blue along with the accompanying bond angles. So now for our molecular polarity, we're trying to decide which of these are dipoles. So in other words, we're trying to decide whether these molecules are polar or nonpolar. So quick refresher, remember that polar means that essentially your molecule is uneven. Your electrons are unevenly shared, okay? A nonpolar molecule means that it's balanced out. So all of the bonds cancel each other out essentially, so that's, everything is sort of equal and opposite. So there are kind of 2 things to look for something to be polar. You want to look at the terminal atoms, so the atoms attached to the center. You also want to look at if there are lone pairs of electrons on the center. So again, if you don't already have it out, have that molecular polarity flow chart next to you, and you can walk through each of the questions for all of these molecules to decide. So if I look at this first one, how many total atoms are in the molecule? 1, 2, 3. There are 3 or more atoms, so the first question we ask is, are there lone pairs of electrons on the center? The answer is yes. So the final question is, are those electron pairs symmetric? Well, I only have 1, so there's nothing for it to be symmetric with. This lone pair is essentially going to make our structure very uneven. If I were to draw that in 3D, it would look roughly like this, and we'd see that that lone pair up there is not being balanced out by anything else. So that means this molecule is a dipole, or in other words, it is polar. Okay, so SO2 would be polar. What about CO2? Well, again, walk ourselves through the questions. Are there lone pairs of electrons on the center? No. Are all of the atoms attached to the center the same? Yes. That means that this one is nonpolar. These oxygens on the outside are essentially pulling equal and opposite outwards on that electron density, making this structure balanced overall. Looking at this one, we have no lone pairs on the center, but we have to answer the question, are the atoms attached to the center the same? No. Nitrogen and oxygen have different electronegativities, therefore they will be pulling with different strengths. That means N2O is a dipole. This is a polar molecule. Okay, so remember that dipole and polar essentially mean the same thing. A dipole is a noun, polar is an adjective, but they're talking about the same thing. For ClO3-, we see here that this lone pair of electrons on the center there are not being balanced out by anything else. So that lone pair of electrons would make this polar. So this is a dipole. And then our final few here. This one also has a lone pair of electrons there, making this a dipole. Again, we're only concerned with the central atom. Now, the reason I drew the structure this way for SCl2 is because if I were to draw it like this, how many of you probably drew the Lewis structure like that? You may look at this and think, oh, those lone pairs are symmetric, because you might say, well, wait a minute, these are completely opposite, so this must be nonpolar. They're canceling each other out. But remember, this is why geometry is important. If this is a bent structure, all of the electron density is up on the top half of this molecule. They are not canceling each other out, because there's nothing down here canceling this out. If you're having trouble visualizing that, I suggest you pull up this bent structure on that molecular shapes simulation we posted, and you'll see that this is not actually balancing out. Therefore, that means that a bent structure will always be a dipole as well. It would always be polar. For our final one here, trigonal planar, there are no lone pairs of electrons on the center, but because these three are different, that means that this structure would indeed be polar. So we have one more dipole here. Okay? So I hope that helped figuring out. The one final thing I want to show you that isn't an example per se, but looking at these are exceptions to sort of what we were just looking at, because both of these molecules, you'll see when you draw the Lewis structure, do have lone pairs of electrons but are actually nonpolar. So take a moment, pause the video, and draw the Lewis structure for both of these molecules. Okay, so if we draw our Lewis structures, they should look like this. I left the lone pairs off the outer elements because we're just concerned with the center. But what I would see that this particular structure, the AX4E2 one, that's square planar. And this one over here would be AX2E3, which makes this one linear. So you may be tempted to look at both of these and say, wait a minute, there are lone pairs of electrons on the center, they must be polar. But if we think about what these actually look like in 3D, I'm going to try my best to sketch these here for you. If we think about what these look like in 3D, these fluorines would all cancel each other out because they're all sort of essentially divided into, four partitions of a grid here. So they're all 90 degrees from each other. But our lone pairs of electrons, one's going to be coming out of the top of our structure, the other is going to be coming across the bottom. So all these fluorines are on one axis and canceling each other out. These lone pairs are on the other axis 180 degrees from each other. So they are actually canceling out. They're balancing each other, which means that this would be non-polar because of that. It is not being pulled in any particular direction. If we look at our other one, if I drew that one in 3D, looks like this. So we have our fluorines, but then one of these balloons is coming out that way. So balloons, for lack of a better name, these are our lone pairs. One's there and one's coming out here. Now it's a little hard to tell flat here. Like I said, you may want to play around with these in the 3D simulation so you can see it. These are canceling each other out because they're 180 degrees apart. These three would be on the other axis, perpendicular to the fluorines, all 120 degrees from each other. So those molecules, those electron pairs are canceling each other out. So if the atoms cancel and the electron pairs cancel, this one would also be nonpolar. So these are the only two exceptions you need to remember. A square planar and linear, so in other words AX4E2 and AX2E3, even though they have lone pairs, those on the central atom, those geometries are indeed nonpolar. Every other structure you come across, if there are lone pairs of electrons in the center, it's polar. These are just the two exceptions.